Hi everyone, this is a video going through our Unit 5 covalent bonding material. So this is great for review or if you missed a day in class to go over this. And I built this screencast around the PowerPoint. So to start us off, Unit 5 is on types of bonds, and so we find the different types of bonds through electronegativity. So we look at the differences in electronegativity, and if anything is, between 0 to 2 for a difference, chances are it's going to be a covalent bond. But we also have to look at type of element, and that's actually really important. So type of element is also really important because you can have a electronegativity difference. You can have a value that has the same electronegativity difference, but you could have two different types of elements, and that can be the determining factor for what type of bond you have. So we have ionic, metallic, and covalent. So we are just going to focus on covalent bonds right now. So a covalent bond is a non-metal bonding with a non-metal. If we need a little review on what a non-metal is, I have a periodic table over here. So non-metals are going to be on the right side of the table. I do not have the diagonal staircase on here. But for example, boron, carbon, silicon, phosphorus, nitrogen, oxygen, sulfur, these are all non-metals down here. All right, so when these are bonded to each other, then you will have a covalent bond. All right, so non-metal. Something that's really important to highlight is that covalent bonds share electrons, okay? They share electrons. Keyword is share. So they share electrons, and their difference in electronegativity is less than 2, okay? You might have one. You might find that there's a covalent bond that's exactly 2, but most of the time their electronegativity difference is going to be less than 2. And then we can have polar covalent and non-polar covalent. We're going to go over this later and be more specific about it. But in a polar covalent bond, the electrons are shared unevenly. And in a non-polar covalent bond, the electrons are shared evenly. And we look at difference in electronegativity to determine whether a covalent bond is polar or non-polar. All right, so really important piece, drawing covalent bonds or Lewis dot structures. So the reason that we draw Lewis dot structures the way we do is because atoms want a full octet. They want 8 valence electrons. That's kind of a main idea for this unit. So they want 8 valence electrons. So one bond equals 2 electrons between shared atoms. I have it drawn down here. So a carbon to hydrogen bond. Okay, so I have 2 different dots. So the carbon and hydrogen are sharing these electrons. We can also use lines to signify bonds. And so a single bond can be shown using a line. So one line equals 2 dots, okay? So now I have my carbon-hydrogen bond and a single bond. I can also use multiple lines to signify multiple bonds, okay? So when I have 2 lines like this, that means I have a double bond, and when I have 3 lines, that means I have a triple bond. Using dots, a double bond is going to have 4 valence electrons, while a triple bond is going to have 6. So you can use whatever method you prefer. The big idea is just making sure that our atoms have 8 valence electrons, okay? So that's why we make bonds, because they have to share in order to have 8 valence electrons. It's important to note, though, that we do have exceptions, okay? We've talked about these in class. So this should not be the first time we've done practice problems with them. But these are really important. So boron only needs 6, okay? Boron can have 6 valence electron, and it can be happy. Beryllium only needs 4, okay? Beryllium only needs 4. Hydrogen can never have more than 2. This is something that's really important. Hydrogen can never have more than 2. Because hydrogen only has 1 valence electron, and so it cannot hold more than 2 valence electrons. And so it will only ever single bond, okay? Hydrogen will only single bond, and it will never have a lone pair. We will never see a lone pair with hydrogen. It isn't possible, because if hydrogen is already bonded, it cannot have any more valence electrons. And then phosphorus can have up to 10, and sulfur can have up to 12. So I want you to make sure when I say up to, I'm saying it can have 8 to 10 or 8 to 12, okay? So it's still happy. If it just has 8 valence electrons, you will find that there are Lewis dot structures where you can only fit 8 valence electrons on a phosphorus or a sulfur, just because you have a limited amount of valence electrons. But it can, those two atoms or elements can have up to 10 or up to 12. So I have a few different Lewis dot examples that we're going to go through together. But before we start that, I just want to remind you of the first step for drawing Lewis structures, which is adding up all the valence electrons that will be in your structure. This is probably the most important step, because if you forget this step, then you could draw your Lewis structure wrong. You could add more valence electrons, or you could have not enough valence electrons. And the number of valence electrons in the Lewis structure also determines how many single, double, and triple bonds will end up being in the structure as well. So I am going to quickly go over how we find the valence electrons for an atom. If you feel really comfortable with that, go ahead and skip that portion to when I start going through the examples. But if you want to review, or you still don't feel very comfortable on finding the number of valence electrons, keep watching this video, or just don't skip ahead. So here's my periodic table. This is what we use to find the number of valence electrons, and we use the column number to figure out how many valence electrons are in an element, okay? So for first and second column, it's really easy, okay? So column 1 is gonna have 1 valence electron. Oop, that's really not great one. Column 2 is gonna have 2 valence electrons. And then we're gonna skip the transition metals, okay? Because they have a different rule. Now, 13 through 18 is a little tricky because they have a tens place. We're just gonna look at the 1 spot, because that will tell us how many valence electrons we have in each column. So I'm gonna highlight that 1 spot. So column 13 is gonna have 3, 14 will have 4, 15 will have 5, 16, 6, 17, 7, and 18, 8. Another way to remember this is that we know noble gases, that is column 18, right? These are, I'm going to highlight them. These are noble gases, okay? That's from unit 4. So here we have noble gases. So we know noble gases have a full octet. That's one of the reasons why they are called noble gases. So we know noble gases are going to have 8 valence electrons, which means the halogens, the column before noble gases, are going to have 7, and then we'll have 6, 5, 4, 3. Okay, so we can start at noble gases and work our way backwards. That's another way to remember. Now, just a reminder, helium, circle that, helium is only going to have 2 valence electrons, okay? Because helium only has 2 electrons, it has 2 protons, so it's only going to have 2 valence electrons. I'm going to draw the Lewis dot of helium. It looks like this. That's one of our exceptions. We don't really use helium a lot in Lewis dot structures, so you don't have to worry too much about it, but I just wanted to remind you that all the noble gases have 8 valence electrons except for helium. All right, so now we're going to do our Lewis dot structures examples. We're going to start with H2O or water. We have looked at this molecule a lot. So remember, our first step is to figure out how many valence electrons will be in our Lewis dot structure. So we have to add up the valence electrons from our atoms. So I'm going to start with hydrogen. Hydrogen has 1 valence electron, and I have 2 hydrogen atoms, okay? So the subscript means I have 2 times 2, which means I'm going to have 2 valence electrons from hydrogen, and then oxygen has 6. So then I'm going to have a total of 8 valence electrons in my structure. All right. Now we're going to get to drawing it. First, we have to set up our atoms. So usually the first atom will be our center atom, or the smallest amount of atoms will be our center atom. So in this case, oxygen, we have the smallest amount of oxygen atoms, so that's going to be our center atom. So I'm going to put oxygen in the middle. The hydrogens are going to go on the outside. Okay. And I'm going to use lines as my bonds instead of dots. If you still like using dots, that's great. Keep doing that. But in this case, I prefer using lines. So now I have to bond them, okay? So remember, 1 line equals 2 valence electrons, okay? So first you have to bond all of your atoms because they have to be connected somehow. And then you are going to fill in the octets for your outer atoms. So you're going to fill in the octets for your outer atoms. So remember, hydrogen is one of our exceptions. So hydrogen can only have up to 2 valence electrons. So now that hydrogen is single bonded, both of my hydrogens have a full octet. So now I'm going to fill in the octet for my oxygen, okay? So if I'm going to count, I have 1, 2, 3, 4, 5, 6, 7, 8. All right, so oxygen has a full octet, and I have used 8 valence electrons. So this is what my Lewis dot structure for water is going to look like. All right, so now I have SH2. So first we have to count up how many valence electrons we have. So S has 6. And remember, hydrogen has 1. I have 2 hydrogen atoms. So I'm still going to have a total of 8 valence electrons. All right. So S is not only my first atom first element in my formula, but it's also the least amount of atoms that I have. So S is going to be my center atom. I'm going to have my hydrogens. I'm going to single bond them. And then I'm going to fill in the octet for sulfur. Okay. So then I have to count. Okay, 1, 2, 3, 4, 5, 6, 7, 8. All my atoms have full octets. They're nice and happy. And I have used the total number of valence electrons that are in my structure. So this is my structure for sulfur SH2. Looks almost the same as my structure for H2O. All right, now we have CO2. CO2 is another Lewis dot structure that we have looked at multiple times throughout this unit. So carbon has 4 valence electrons, oxygen has 6. We have 2 oxygen atoms. 4 plus 12 equals 16 valence valence electrons. Okay, so carbon is going to be my center atom. My oxygens are going to surround it. So first what we have to do is we have to start by single bonding my oxygens to my carbons. And then this is going to be a little different than how I originally taught to do Lewis structures. So first what I'm going to do is I'm going to fill in the octets for oxygen, okay? So my oxygens, to fill in their octets, I'm going to put in lone pairs. Okay, so reminder, lone pairs are 2 valence electrons that are not used in bonding. Now I'm going to count how many valence electrons I used after I have completed the octets for my outside atoms. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have used 16 valence electrons, and that is the amount I have to make my Lewis dot structure. However, carbon does not have a full octet. Right now, it only has 1, 2, 3, 4, which means I need to delete some of my lone pairs and create a double or triple bond. So it doesn't matter which lone pair you delete. I'm going to do my outside ones just because that's what I want to do. So I'm going to make a double bond. And then now carbon has 1, 2, 3, 4, 5, 6. And so now I'm going to delete a lone pair on my other oxygen and create a double bond there. So now, counting, I have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've used my 16 valence electrons. Oxygen has 8 valence electrons. Carbon has 8 valence electrons. So now they're all happy, okay? This is my Lewis dot structure for carbon dioxide. All right, now we have Ni3. If you feel really comfortable with these Lewis dot structures, go ahead and start, doing this example without me. So pause the video, and then when you're finished, play it and see how you did. So first, we count how many valence electrons we're going to have in our structure. So nitrogen has 5 valence electrons. Iodine has 7 times 3, because I have 3 iodine atoms. That is a weird 3. Equals 21. 21 plus 5 is 26 valence electrons. All right, so now nitrogen is going to be my center atom because it has, it's not only the first atom in my formula, but it is also the least amount. So I have 3 iodines and only 1 nitrogen, so nitrogen is going to be my center atom. And then I'm just going to place my iodines around it. It doesn't really matter where you place them. I try to make it even, but again, it doesn't matter. And then I'm going to single bond them. And now I'm going to fill in the octets. So this is where it gets a little tedious because I'm drawing a lot of dots. But it's really important you don't forget to add the lone pairs onto your outside atoms. So before I add any more lone pairs, I am going to count how many valence electrons I've used. So right now, only iodine has a full octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So right now I've used 24. Iodine has a full octet. I still have 2 more valence electrons that I can place. And so I am going to place them on my nitrogen. That's the only place that I can place my lone pairs. Plus, nitrogen doesn't have a full octet yet. So placing those 2 valence electrons are going to complete the octet for nitrogen. So now I've used 26 valence electrons. Each of my atoms has a full octet, and so this is my Lewis structure for Ni3. All right, now we have CCl2F2. So this was an example that was in our VSEPR model lab, and it was confusing to a lot of people, and I don't blame you. And the trick was just figuring out what the center atom is. So first we have to count up our valence electrons. So carbon has 4, chlorine has 7. I have 2 chlorines, which equals 14. And fluorine also has 7, and I have 2 fluorines equals 14. So 14 plus 14 plus 4. So 14 plus 14 is 28 plus 4 equals 32 valence electrons. Now, the trick here is that carbon is going to be our center atom, okay? Looking at this Lewis structure, we have 3 different types of atoms in here, and that is confusing. But again, we're going to use our least amount, so the smallest amount that we have as our center atom. So in this case, it's carbon. So carbon's going to be my center atom, and then I'm just going to place the chlorines around it and the fluorines around it, okay? And then I'm going to single bond them, and I'm going to add lone pairs to my outside atoms. All right, so now all of my outside atoms have a full octet, okay? Carbon even has a full octet, and now I want you to pause the video and count how many valence electrons that you have placed. So if you pause the video and you counted how many valence electrons you've placed, you would have found that you have placed 32 valence electrons. So this is the Lewis dot structure for CCl2F2. All right, so now we're going to talk about naming covalent or molecular compounds. And so when we name molecular compounds, we use prefixes, okay? So we always have a prefix for our first element unless we only have one atom for our first element. We will just have the name for our first element. So we're never going to have a mono nitrogen, okay? We're never going to have mono oxygen for our first element. If we only have one atom in our first element, it's not going to get a prefix. But then we always have a prefix for our second element. And then we cut off the ending, and we're going to have IDE at the end. So here are the prefixes that I wrote down for you. You do have to memorize these, okay? So if you haven't already, make flashcards. It's really important you memorize them. So we're going to do some examples together. So I have NO. So I have one nitrogen atom. So I'm not going to have a prefix because one is mono. So one nitrogen atom is going to be nitrogen. And then I have one oxygen atom. So that is going to have a prefix of mono. And then I drop my ending of oxygen and add IDE. So NO is nitrogen monoxide. NO2 is going to be very similar. So I have no prefix on my first element. And then I'm going to add a 2 or di for my second element. So instead of monoxide, I'm going to have dioxide. N2O4, now that I have more than one atom in my first element, I'm going to have a prefix for my first element. So it will be dinitrogen, tetra oxide, or tetra oxide. It gets a little tricky when you have two vowels right next to each other with prefixes. So you can either write tetraoxide or tetroxide. I am not going to be super picky on it, but you may have chemistry teachers in the future that will be. lastly, I have S9H7. So the prefix for 9 is nona. The prefix for 7 is hepta. So I'm going to have nona sulfur hepta hydride. So it's kind of a mouthful. It looks a little weird, but as long as you follow the prefix with the IDE ending, you'll be golden for naming. All right, so now we're going to talk about polarity. So we can have a polar covalent or non-polar covalent bond. A polar covalent bond shares electrons unevenly, okay? So the electrons are pulled more towards one atom than the other. And a non-polar covalent bond means the electrons are shared evenly. To find whether a covalent bond is polar or non-polar, we look at the electronegativity difference, okay? So 0 to 0.4, it's non-polar. 0.41 to 2 is polar. To find the difference, we subtract electronegativity values. And if for some reason you get a negative value, take the absolute value. So that means take the positive value. I added a periodic table with the electronegativity values on here, okay? This is the periodic table you will have in class to find the values. So this is what the values we take to find the difference. So let's look at whether we have polar bonds in our Lewis dot structures we just made. So for H2O, when you have multiple bonds, you only have to look at each bond on its own, okay? So we're gonna look at the hydrogen to oxygen bond. So I'm gonna go to my periodic table with my values on there. So oxygen has a value of 3.5, hydrogen has a value of 2. It doesn't matter what order you put them in. So 3.5 minus 2.1 is equal to 1.4. That is much larger. Ooh, that is not a 4. 1.4, which is much larger than 0.4. So that means that my hydrogen to oxygen bond is polar. All right, so now let's look at a hydrogen to sulfur bond. So hydrogen, again, has a value of 2.1. Sulfur has a value of 2.5. So we're going to do 2.5 minus 2.1. That is equal to 0.4, which means since it is 0.4, that is right on the cusp, and we decided that 0.4 is going to be non-polar. So this is going to be a non-polar bond. And if you need a calculator to do these, like, please grab one. I would rather you have a calculator and feel comfortable about your values than not use a calculator and get incorrect values. All right, so now we're going to do oxygen to carbon. So when I have a double or triple bond, that does not change the value of my electronegativity difference, okay? So oxygen to carbon bond. Oxygen is 3.5 minus carbon, which is 2.5, equals 1, which is larger than 0.4. So this is a polar bond. Okay. Ni3. So we're going to look at a nitrogen to iodine bond. see. So nitrogen has a value of 3. Iodine has a value of 2.5. Which means the difference is 0.5, which is larger than 0.4. So nitrogen to iodine is a polar bond. So each of these 3 bonds are polar, covalent. Okay, lastly, we have CCl2F2. So now we have 2 different bonds. We have a carbon to chlorine and a carbon to fluorine, okay? So we're not going to add these differences together. We are just going to look at each of these bonds separately on their own. So carbon has a value of 2.5, chlorine has a value of 3. So 3 minus 2.5 equals 0.5. So this is a polar bond. Fluorine has a value of 4. So I'm going to do 4, because again, it does not matter what order I put my values in. 4 minus 3 is equal to 1. So this is also a polar covalent bond. So in this case, each of these atoms are polar covalent. They have different polarity values, but they are still all polar covalent. So we like to look at molecular polarity. So is the whole molecule polar or non-polar? So in order to have a polar molecule, you have to have polar bonds. So we look at each bond on its own. So like the C2Cl2F2, we look at each bond separately. But big thing, if we want, or if we have a polar molecule, that means polar bonds are present somewhere within the molecule. If you have a non-polar molecule, it means you have no polar bonds, or you have polar bonds, but the molecule is symmetrical and has no lone pairs on the central atom. So to see if a molecule is symmetrical, we're actually going to look at VSEPR. So I'm going to go through VSEPR, and then we'll come back and see if our Lewis dot examples are polar or non-polar. So VSEPR is the valence shell electron pair repulsion theory, and VSEPR tells us the 3D shape of a molecule, because as a reminder, molecules are 3D. Even though we draw Lewis structures as 2D, they are 3D. So we have linear, which means we have 2 atoms bonded to a central atom. So linear can look like 2 different things. We can have a linear that looks like this, so just 2 atoms bonded together. We can have here. We can also have any of these forms in double or triple bonds. The key here is that we have 0 lone pairs on the center atom, okay? And we will have a bond angle of 180 degrees. Bent is when we have 2 bonded atoms to a central atom, and we have 1 to 2 lone pairs on a center atom. So that's going to look something like this. And right now I'm going to put 1 lone pair. We can also have it looks like this. Remember, because lone pairs still take up space, and so they are going to push those bonded atoms down. And lone pairs have a bond angle of less than 109.5 degrees. All right, and then we have trigonal planar. Trigonal planar is 3 atoms bonded to a central atom and 0 lone pairs. So that will look something like this. Okay, so we have 3 atoms bonded to a center atom. We have no lone pairs. and we're gonna have a bond angle of 120 degrees, okay? So this will be 120, this will be 120, and this will be 120. And the key word is planar, okay? Planar means flat. So when you're looking at this molecule, it will be flat, whereas trigonal pyramidal is going to look kind of like a pyramid, like the name. And we have 3 bonded atoms to the central atom, and 1 to 2 lone pairs. So that's the big difference between trigonal planar and trigonal pyramidal, is that pyramidal has lone pairs on the center atom. So here we are. So we can have something like this. We can have something like that. Okay, so those will all be trigonal pyramidal. And the bond angle for trigonal pyramidal is going to be 107 degrees. Next, we have tetrahedral. Tetra means 4. So we will have 4 atoms bonded to the central atom and 0 lone pairs. This one is a little bit harder to draw 2D to show the 3D shape. So this is my best drawing. And it has a bond angle of 109.5 degrees. Trigonal bipyramidal has 5 atoms bonded to the center atom and 0 lone pairs. We're actually going to have 2 bond angles for this. So we're going to have 2 vertical bonds, and then we'll have 3 kind of planar or equator bonds. So the bonds on the equator, so these guys, I'm going to redraw them in red, are going to have a bond angle of 120 degrees. And then the vertical bonds have a bond angle of 90 degrees. Lastly, we have octahedral. So octahedral is a little tricky because we have octa, which means 8, but we have 6 atoms bonded to the center atom. So an octahedral is going to look like 1, 2, 3, 4, 5, 6. Again, octahedral is a little bit tricky to draw 2D, but there's only going to be 1 bond angle, and all the bond angles are 90 degrees, okay? So the reason why I went through VSEPR before going through molecular polarity is that some of these shapes can actually determine whether the molecule is polar or nonpolar. So linear, because a linear is straight, this is actually perfectly symmetrical. So linear will be nonpolar. Trigonal planar will be nonpolar. Tetrahedral is nonpolar. Trigonal bipyramidal is nonpolar. And octahedral is nonpolar. So these are only nonpolar if all of the outer atoms are the same, or we have like a similar, an even amount of outer atoms. So when I say that, let's look at our example over here. We have C2, Cl2, F2. So we have polar bonds, but because we have 4 atoms bonded to the center atom and no lone pairs, this is tetrahedral. Which means that all of our bonds or our dipole moment, our polar bonds are going to cancel out. So this is going to be a non-polar molecule. Now, if you feel really comfortable with this and you want to do more practice, go through our examples, our Lewis dot examples, pause the video, but I'm going to go through the rest of them. So I'm going to identify the shape, whether it is a polar molecule, and then I'm also going to identify the bond angle. So tetrahedral has a bond angle of 109.5 degrees. All right, let's look at Ni3. So we have 3 bonded atoms. We have a lone pair on the center atom. So this is trigonal pyramidal. And we have polar bonds. We have a lone pair on the center atom. So this is going to be a polar molecule. And the bond angle is 107 degrees. All right. Next, we have CO2. CO2 has 2 atoms bonded to the center atom. No lone pairs, so this is going to be linear. We have polar bonds, but again, we don't have a lone pair on the center atom. And linear is one of our nonpolar molecules, so this will be nonpolar. And linear is a good way to show this. So if I were to draw the dipole moments, okay, so these arrows, pretend they're exactly the same length. If I were to shift these arrows on top of each other, nope, that's not gonna work. Okay, if I were to shift these arrows on top of each other, they would cancel each other out, okay? So that's why we get nonpolar molecules. So even we can have polar bonds, but a nonpolar molecule. And then the bond angle is 180 degrees. All right. I'm going to do H2O and SH2 together because they're actually going to be the same shape. So they have 2 bonded atoms to the center atom and 2 lone pairs. So these are both going to be bent. They will be polar. Oh, wait, actually. So H2O will be a polar molecule. SH2 is going to be a nonpolar molecule because I do not have polar bonds. Okay. My hydrogen to oxygen bond is polar, but my hydrogen to sulfur bond is not polar. All right, so H2 is a polar molecule, SH2 is a nonpolar molecule. They're both bent, so their bond angle is going to be less than 109.5 degrees. All right, lastly, I'm going to practice naming these. So if you feel comfortable naming, go ahead, pause the video, go through these examples, name them, and then play the video. So H2O, I have a subscript of 2. I have no subscript on my oxygen, so it's going to be dihydrogen monoxide because I have to get rid of the ending on oxygen and replace it with "-ide". SH2, I have no subscript on my sulfur, but I have a subscript of 2 on my hydrogen, so I'm going to have sulfur dihydride. Okay, I don't use a prefix of mono on my first element. CO2 is going to be similar. I'm going to have carbon dioxide. Ni3 will be nitrogen. It's not how I spell it. Nitrogen triiodide. Okay. And then I am not going to name CCl2F2. We never learned how to name a molecular compound with 3 different elements, and so I'm not expecting you to be able to name this element, okay? So we're gonna leave that blank. All right, one thing I forgot to go over or write down is IMF, or intermolecular forces. So intermolecular forces are how molecules stick together. And we looked at 3 different types. We have dipole-dipole, hydrogen bonding, and London dispersion. So dipole-dipole and hydrogen bonding both occur between polar molecules, while London dispersion occurs between nonpolar molecules. So dipole-dipole occurs when we have a partial positives and partial negatives on a molecule. So these are going to be my little molecules, okay? And because we have polarity, the electrons are going to be attracted more to one side of the molecule. So for example, we'll have a partial positive and a partial negative, and same thing on a different molecule. And so those partial charges are going to be attracted to each other. So that partial positive is going to be attracted to that partial negative. We can put another molecule in. Yes, that's going to be attracted to each other. Yeah, so that's dipole-dipole. Hydrogen bonding occurs, again, between partial charges. But in this case, a hydrogen with a partial positive charge is involved. So again, if I were to draw some imaginary molecules, okay, so our hydrogens have partial positive charges because they're most likely the least electronegative atom. So they will be attracted to those partial positives. And then we have London dispersion. So London dispersion occurs between nonpolar, and that happens through temporary partial charges, okay? Temporary is the key word. So London dispersion is going to be weaker than dipole-dipole and hydrogen bonds, okay? That's something important to know. But also, I want you to take note that dipole-dipole, hydrogen bond, and London dispersion, those are all occurring between, both polar or non-polar molecules, okay? So that means that polar mixes with polar. Non-polar mixes with non-polar. Oh my gosh. Polar does not mix with nonpolar, okay? Because they don't have those partial charges with each other to attract, to stay together, okay? Like Nonpolar has temporary partial charges, but it is never going to have enough in order to connect with or stick together with a polar molecule. So that was a quick run through of intermolecular forces, or IMF. And this video was a review of covalent bonding. If you would like to get more practice in, I have all the worksheets that we've done throughout the unit on Canvas, so you can print those out. You can do them electronically on scratch paper. And then I also have the study guide on Canvas. The study guide is not a complete review, but it is a pretty good idea of where you're at and how you will do on the test. So really big thing is understanding intermolecular forces. You're going to have a question on that. Being able to determine whether a bond is polar or nonpolar, and then whether the molecule is polar. So memorizing VSEPR, memorizing those bond angles, being able to, if you understand that having a lone pair on a center atom can determine molecular polarity, that's good. But if you also want to memorize the nonpolar VSEPR shapes, that also might be a good idea if you have some time. Naming a molecular compound is really important. And being able to build Lewis dot structures. If you are really trying to cram things in, first do Lewis dot structures, okay? Because that is the foundation for covalent bonding. If you have any questions, you can email me or come in during Patriot period.